I would now like to introduce a new quantity that we use to study electrostatics. And this quantity is called the electric flux. Okay, so to motivate this, I want to consider a couple of different situations, and then after I look at a couple of different cases, I'll tell you what the definition of this new quantity is. All right, so let's imagine that we have some constant electric field in some region of space, which I'll just draw some electric field lines like this. Okay, and let's say that I draw some surface in that same region of space. I'll just draw a little rectangle in perspective like this. Okay, and I get to pick the direction of the area vector to be perpendicular. It could either be to the left or to the right. I will pick it to be to the right. Okay. All right, so in this case, there is a lot of electric field passing through the surface. If I imagine that this was like some sort of net trying to catch the electric field going through, that area vector is catching a lot of the electric field. So there's lots of electric field going through the surface. Okay, so now let's imagine that you rotate the surface a little bit. So if I have my electric field like this, and I'm just going to have rotated this something like that, and now I have my area vector pointing kind of like that, perpendicular to the surface. Hopefully the perspective doesn't seem too weird there. Here I have less electric field. Still some is passing through, but less. Oops, let me change colors here. So less electric field through surface. And then in the extreme case, if I have my electric field like this, and I put the surface like so that the area vector is perfectly downward, well, now we can see that there's no electric field to the surface. Because instead of going through, it's going along the surface. Okay, so we can make a distinction between these three cases by trying to figure out a way to characterize the amount of electric field going through the surface in each case. Okay, so that quantity we call the electric flux. Okay, and we represent it with the Greek letter phi, and because there's more than one kind of flux, phi e, for now we have just the electric flux, and so we'll just call it flux sometimes, but know that we are specifically talking about electric flux. Okay. Later on, we'll have some other kinds, and we'll want to be really careful not to mix them up, but for now it won't be confusing. Okay, so the definition is that the electric flux is equal to E dot A. Okay, where remember, the dot product is E, A, cosine theta. Okay, so E and A are the two magnitudes. They're always positive. Cosine theta can be positive, negative, or zero, depending on the angle between E and A. Okay, so if E and A are in the same direction, like in the first case, then we have a large flux. If they are at some angle, then they have a smaller flux. If they're perpendicular to each other, that means the electric field's going along the surface rather than through it, and we get a flux of zero. Okay, so we can interpret this as the amount of electric field going through the surface. Okay. We can also integrate over a curved surface if we want to. So we can also do electric flux is equal to the integral of E dot dA So then we just split up the surface into small little areas and then calculate a small amount of flux for each piece and then add them all up. Okay, so that's a thing that we will also do sometimes. We can also think about this as counting the number of field lines going through the surface. So in the first case, I have a couple of field lines going through. In the second case, there's one. In the third case, no field lines actually pass through the surface. So that can be a really nice shorthand to at least check your work, even if it's not quite as rigorous.